Got to be double checking. Yep. So it's all looking good. All right. Um, okay. So what we're going to do today is we are continuing to talk about, writing code in TTP ASM. And by the way, exam 2 is graded, so you guys should have your score. It's the aggregated score. I do have, comments and all the breakdown of all the points. So if anyone is interested, I can always, either discuss that with you or I can send, that to you also. Um, all right, with that said, are there any questions about the previous lab, which is the absolute value lab? No questions? All right. So if there are no questions, we're going to talk about calling and returning from subroutine today. And then we do have an extra lab today, which is compiling C control structures. So the lab has to go back to what we talked about last Monday. But the topic is a new topic. And this is a kind of important topic because what we are finally doing is to correlate what we are learning in this class with your other classes, because now we are actually starting to look into how C code compiles into assembly code. Now, when you look at the actual example, it is using TTP ASM, which is specific to this class. I promise, after this class, you will not see TTP, ever again. Okay, that's just a tool that I developed for teaching this class. However, you will find assembly language programming in many other classes, and as a result, it's going to be quite interesting. And then the other thing that's also going to be useful is what we had started to talk about now is applicable to general C, C++ programming. Because you can run into problems in C, C++ programming where the symptom of a bug cannot be explained using just C or C++ alone. You can call a subroutine, and when it returns to a function that you never call in a program. You can also return from a subroutine, and then you find all your local variables shifted. So let's just say that you declare variables x, y, and z in the caller. You call the subroutine works just fine, did not crash or anything, return to the caller, and then now suddenly you find out that variable x is variable y is variable z, and variable z has some kind of random value in it. You can also experience problems like you return from a subroutine, but instead of returning to exactly where it was called, it returned to a few lines before or a few lines after. So without this part of this class and exactly what we're going to talk about for the next few weeks, it'll be very difficult for you to find out what went wrong with the program. So that's why what we are going to talk about now actually has a lot of relevance to C, C++ programming. If you program in Node or Python and stuff like that, it may not affect you nearly as much. But if you program in C, C++, this is really important topic. All right. So what we're going to talk about is how to call a subroutine and how to return from a subroutine. So right here, you can see there's a C program. This is just strictly in C. We have a void function f, which doesn't do a single thing. Okay, it does not return a value, and there's nothing to do. Okay, it's perfectly okay to write subroutines like that. It's just that it doesn't do anything. In the main function, we call f twice, and then we return from the main function. So at this point, you will ask, okay, so what is the whole point of this program? Well, there are a few things I want to illustrate. The first thing is going into a subroutine is pretty easy. JMPI will get the job done. Okay, so if we define f, function f with a label of f to mark its beginning of execution, not a problem. Okay, going from the call, which is line 7, to function f, that's easy peasy because we can use JMPI f. But coming back is a problem because you would think, when function f is returning, we know kind of where to return to. We have to return to line 8. But that is a problem because what if you call function f again, but this time it has to return to line 9? In other words, where a subroutine has to return to depends on where it got called. Is that okay? So a JMPI won't do the trick because JMPI says I can only go to one place, okay? And that place has to be determined at the sample time. But when you return from a subroutine, where it needs to return to cannot be determined at the sample time. Are we okay so far with that concept? Because that's the biggest puzzle is how do we solve this particular problem? So the solution is stack, okay, the stack. So what we're going to do now is we're going to take a digression to talk about the stack. So we'll start with the beginning. I know the screen is kind of wide. It's harder to read sentences that way. So I'm going to highlight here what is important or what I'm going to talk about next. So the first thing is a stack is what we call a LIFO or LIFO, last in, first out kind of data structure. Last in, first out means it is kind of like a U-Haul truck. Okay, if you ever have moved using a U-Haul truck, you will remember that the very last thing that you push onto the truck and then you slam the tailgate and you shut will be the first thing to fall out of the truck when you open the tailgate again, because when you drive, things will shift around and even though it wasn't about to fall off, when you put it into the truck, it's going to fall off, okay, when you open up the tailgate. Does that make any sense? So that means, if you put the map of your destination, like the first thing into the truck, good luck, getting it back out of the truck, when you get, if you need it. So last in, first out, in real life is not used a lot. Okay, another good example would be the plates at a buffet place. Okay, so when they bring out, like a whole bunch of new clean dishes and they put it onto that track, put it onto the either the tray or the stack. Um, the first plate that you're going to take out would be the last plate that get put onto the stack. Does that make any sense? Okay, so it's last in, first out. So we're going to illustrate, what we can do to implement it, and this is the C code to implement last in, first out. So the first thing we do is we define a stack size. In other words, how many items can we store on the stack? I'm only using 32 here, just as an example. The next thing we do is we actually declare the stack. So the stack is, in this case, 32 bytes, okay? Because uint 8_t means it is an unsigned 8-bit integer, which otherwise is known as a byte. So we have a 32-byte stack in this case. Now, how we keep track of, where am I supposed to put the next item onto the stack? That is managed by SP, which is the abbreviation of stack pointer. Is that okay so far? Just looking at the C definition that is being highlighted right now. Okay, so good. All right. So now we have to define two operations. The first operation is how do you save an item on the stack? In other words, how do we push an item on the stack? This is how we do it. I know it looks really kind of awkward, but that is how we push an item on the stack. First, we decrement the stack pointer, and then we put the item that we want to save on the stack to the location that is pointed to by the stack pointer. So this is where things start to get a little bit difficult to understand, and it might help, if I use a spreadsheet for this purpose. So let me go to the drive and go to, okay, I have to resort by name. So go to CISP310, go to the shared folder, and then go to examples. And this will be a file that you can see right away if you go to the shared folder. So I'm going to use a spreadsheet for this because I'm just going to use a table to represent this. And I'm going to name the spreadsheet as the stack example. There we go. All right, so the first thing I need to do is to give each location a name. So in the case of using stack, all I'm going to do is to name the actual array element. So there are a few ways to do this. If I use equation, I can kind of make it pretty easy to do. So I'm going to use concatenate, which is a string function. And when you do concatenate, you can basically specify strings to be concatenated together. So the variable or the array is called stack. I'm going to use I'm going to use the bracket notation to indicate which element I'm trying to specify here. And then I specify the index. So the way I draw the stack and the way I draw memory is, if it points up, it's going in higher location. If I point down, it is going to lower location. Okay, so that's a consistent way for me to draw both memory content as well as what is in an array. So in this case, I need this to be 31, and we have a 2, so that means we have to use 34 minus the row number, 33 minus the row number. There we go. And then followed by close square bracket. Let me see. That looks good, right? I mean, so now all I have to do is to kind of copy this all the way down. And now we have the stack, displayed like this. Do we have any questions about what I have done with the spreadsheet up to this point? All I want to do is to show you a quote-unquote map of the items inside the stack array. Is that okay? All right. So what this means is, assuming the stack pointer used to point here, okay? This is where it gets a little bit difficult to kind of explain this, is if the stack pointer was pointing here, okay, when we push an item, the first thing we need to do is to move the stack pointer down, okay, by one location. So what we end up doing is to copy and paste this over here. And then whatever value we want to store to, in this case, stack 28, is going to be put to wherever the stack pointer is pointing to. Is that okay? I know there are many questions in your head. It's like, why do we start from the beginning of the array? Why do we start at the end? Okay, that's a very natural question. Most people have that question when I demonstrate how we are growing the stack, because we're starting from the end of the stack and then we're moving kind of backward to the beginning of the stack. It will start to make sense when we are referring to the variables or parameters and local variables on the stack. But right now, we just have to kind of say, yeah, that's kind of how we do it. All right, so if I switch back to the notes here, this is how we push an item. This is how we save an item on the stack. And the way we retrieve an item from the stack is exactly the opposite. So this is the code that we use to retrieve an item from the stack. So what this means is, if I want to retrieve an item, the first thing I do is just go straight to where the stack pointer is pointing to and say, hey, stack pointer, what are you pointing at? Give me that. I will retrieve that and put it into a variable somewhere. And then what I do is I will increment the stack pointer. So you can see how these two operations are exact opposite of each other in many ways, more ways than one. And let me turn off. It's not a turn off thing, it's just reminding me that I need to go to lecture, which I'm already in right now. All right, so the push item, the push is to decrement the stack pointer and then store a value to wherever the stack pointer points to. To retrieve or to pop, okay, is exactly the opposite. We take whatever the stack pointer is pointing to, copy the value of that location, and then we increment the stack pointer. Are we doing okay so far at this point? So the stack pointer is a bookmark, okay? That's basically what it is. It is a bookmark to say, hey, what is the last location that we use on the stack? That's what the stack pointer is trying to remember. What is the last location that we use on the stack? So when we push an item, what we're trying to do is to say, I'm not going to overwrite that location because I just put something over there. So the first thing I need to do is to quote unquote allocate or flip the page back a little bit so I can start with a new page. That's what SP minus minus is trying to do. It is basically going to a location that is now available for me, and then I put whatever item that I'm supposed to push onto that location. To retrieve or to pop is exactly the opposite, because remember, the stack pointer is a bookmark that points to the last page that was used. So now I go to that page and go like, okay, what is the content of that page? Let's copy that. Go to the photocopier, make a copy. And then what I can do now is to say, that's not needed anymore. So let's increment the stack pointer so that the location that it used to point to is once again available. Is that okay? Sort of? Okay. So what we'll do is I'm going to go back to the example here. The difficult thing to do is it's hard for me to illustrate, how the dynamic thing what happens when I push and what happens when I pop. And I think I got a good way to kind of illustrate it. The first thing we need to do is to figure out how do we initialize the stack pointer. The stack pointer is initialized like this. And so remember this part here. And actually, I'll do something better. I'm going to copy this and put it into the spreadsheet. So this way I can now say this spreadsheet here, this is what it's trying to do. This is what it's representing. And now the question is, where do you think the stack pointer is pointing to at this point? Nope, wrong way. Need to new row above. There we go. So if I were to use column B to indicate where the stack pointer is pointing to, where do you think it is pointing to? Still got a problem because where's oh, I see what the problem is. I do need to insert a row above, but then I have to change all the equations because I was using a equation method to do the calculation. 34. No, this one needs to change to 34. There we go, and there we go. Okay. All right, so let's get back to the question. Where do you think the stack pointer should point to? Which row should they point to because of the initialization? So this is also testing whether you understand pointer arithmetic from CISP310, unless that topic was never covered. Okay, that's a good guess. Okay, so let me just kind of point out what this particular statement means in a slightly different way. It is basically the same thing as saying, SP is the address of stack size. Okay, there we go. So these two statements are identical in terms of what they're doing, but the question is, where is it pointing to? Which row is the stack pointer pointing to at this point? Remember, stack size is 32. If you guys are looking at this and go like, but we don't have an element at the index 32 because that means we're going to be pointing at the location after the end of the array. If you're thinking about that, you are actually correct. That is exactly how we initialize the stack pointer, which is just one item past the end of the array. Okay, so that means the row 2 is where the stack pointer is going to point to. So I'm just going to use this symbol here to identify that the stack pointer points to this particular location. And all of you guys are thinking, but this is bad because we are pointing to a location that is past the end of the array. But if we put something there, that would have been bad. If we were to read that location, it would have been bad. But we are doing neither, right? All we're trying to do is to say, here's a pointer, and it points to that location. And that location turns out to be just one byte past the end of the array. There's no harm done, okay? There's no harm done. It's just like, why would you want to do that? That's the only question that you might have in your head. Are we doing okay so far? Okay? So what I'll do is I'm going to use, it's going to be like an anime. So what I'm doing is I'm going to duplicate this particular spreadsheet and call this one sheet 2. And it's going to represent the next operation. So the next operation is I'm trying to do a push, okay? I'm trying to save a value on the stack. And let's just say the value is 5, okay? That's what I want to do. So the next question is, I'm not really sure what push means, right? So let's go back to the notes again to take a look at what pushing is entailing. Pushing means we have to first decrement the stack pointer, and then we copy the value, which in this case is 5, to where the stack pointer is pointing to. Okay, so let's get back here. So what that means is the first thing I need to do is to move the stack pointer down, right? Because I'm decrementing the stack pointer. So now the stack pointer finally points to a location that is indeed a part of the array. Are we good so far? And then what do we do? What is the second thing that we have to do when we push a value? We store that value to where the stack pointer is pointing to. Okay, well, that's not too hard. I mean, that's all. That's what we're going to do. Are we doing okay so far with sheet 2, which is kind of like step 2 of this animation? We good? All right.
So push 5 just means that we're storing 5.
We are storing 5 to the stack. So what you can do is you look at the stack as a way for you to stash away items that you might need later on, and it's using the order of last in, first out. And that is the only part that is important, is last in, first out. The actual mechanism can change, okay? When you get to CISP310, you might learn, oh, we can use a linked list, okay, to do, to implement a stack. You can also use a vector to implement a stack. It doesn't really matter that much at this point. We are using the most basic and the most efficient way to represent the stack, which is basically just to use a pointer to tell us where the top of the stack is. Are we good so far? All right. So we're going to duplicate sheet 2 and make our third sheet. Okay, so we call this sheet number 3. And this time I'm going to push something else again. So this time I'll push the 17. All right, so remember what we have to do. First thing is to move the stack pointer. Okay, we're decrementing the stack pointer. So that means it's pointing to a location that is earlier than before. And then we copy the value, which in this case is 17, to wherever the stack pointer is pointing to. So 17 goes here. Are we still good so far? Yes? Okay. So we're going to push one more time. Okay, so I'm going to duplicate sheet number 3. And it becomes sheet number 4. And this time I'll push one more time, and we'll push yet another value. I think 2 is fine, okay? So now we have to move the stack pointer again, decrement, and then copy the value 2 to wherever the stack pointer is pointing to. Are we good so far? All right. So let's do some popping. In other words, give me back some value that I saved earlier. Is that okay? So the next one is going to be a pop operation. So we'll duplicate again. So this time we have a pop. So we usually with a pop operation, you want to indicate who is going to be using the pop value. Okay, so typically you have an assignment like x equals to pop something like that. So we will just pretend it as a variable x that's going to store the value of the pop operation. So now we go back to the slide, to the lecture note here, and the first thing we need to do is to go to where the stack pointer points to, retrieve the value at that location, and then x gets that value. Okay, so let's go ahead and say the stack pointer is pointing to a value of 2, so we end up with x getting a value of 2. That's the first step. What is the second step? Let's go back here. What is the second step here? To increment or to deallocate that location. So now we basically just move the stack pointer back up again. So one thing you would notice is the 2 is still here. Okay, because all we are doing is to move the bookmark. All we are trying to do is to say, so you can kind of consider the stack pointer being a bookmark. So everything after the bookmark is still in use. Everything before the bookmark is now free to be reused again. Is that okay? So the stack pointer is really just a bookmark. That's all it is. Yep.
So can you not go back and forth? Can you not go back if you wanted to get 2 again? Can you not go back down?
You cannot rely on that 2 again. So let me see if I can find a prop here. This is good. I got a stack of cards here. And I'm going to use one card and paint it red. So it becomes the stack pointer. Okay? So got a stack pointer, and it's moved. I have to move it around. When I push and pop items. So I can see the bookmark is indicating, things. Okay, so let me designate what is before and what is after. So this is before, and that means lower memory locations. So these are still available. I can still write stuff on these things. What is after? Okay, if I were to hold this sideways, this is better. So what is after, which would be this portion of the stack of cards, those are at a higher location. So they're either at where the bookmark is, or they are at a higher location. So these, I cannot change. Okay, they're supposed to be unchanged. Is that okay? So you might say, but Tech, remember this card here? It has a value of 2, and it still has a value of 2, even though I moved the bookmark to one page after that already. Yes, that's what I did. So now what you need to do is to imagine, this part does require a little bit of imagination, is imagine there are gremlins or ghosts and other supernatural creatures. And what they do is to say, hey, anything that is in front or lower than the bookmark, they can come in and just make random changes to those locations without you knowing them, actually making those changes. Is that okay? I know it sounds really kind of awkward, but that's basically what it is. So in terms of the stack, so in this case, anything that is at stack index 29 and before, they are now susceptible to being changed by these gremlins. Magical creatures, and they can do these changes without you knowing it. Is that okay? So the bookmark is kind of really important because it's kind of like a talisman. It protects everything that is after the bookmark from being modified by the gremlins in this case. Is that okay? I'll explain what the gremlins are later on, obviously. This class is not about superstition, but for now, that's the best way to explain it. Is that okay? So even though we left behind a 2 here, the moment we move the stack pointer to stack 30, this 2 is now susceptible to being modified by the gremlins because it is after the stack pointer, or I should say it's before the stack pointer. Are we good so far? All right. So that's one operation, and we'll go ahead and push again. So this time, I'm going to use the next one. Well, let's do another pop. Okay, let's do another pop, and then we'll push again. So we have, this is sheet number 6. And this time I'm going to say y equals to pop again. All right. So what are we going to do again with the pop operation? What is the first thing to do? Go to the location that the stack pointer points to, retrieve the value at that location, use it, in this case, put it into local variable y. Okay, so the first thing we do is to say, y equals to whatever the stack pointer points to, which is 17. And then we move the stack pointer. So the stack pointer is now incremented to point to the 5. So right now, both 17 and 2, or I should say stack 29 and stack 30, both of those locations, as well as every location before those 2 locations, they are now all susceptible to being modified unknowing to you by these gremlins. Is that okay? So we'll do one more push just so that we know what your push would do again. Okay, so we have another push operation, and this would be sheet number 7. So let's say this time we push again, and this time we push 51. Okay, so if we push 51, we have to kind of look up what are we supposed to do when we push. First thing is to decrement the stack pointer. Okay, that's what push is supposed to do. So it's going to move the stack pointer back to this location. And then the second thing is to store the value, which is 51 in this case, to the location that the stack pointer points to. So this becomes 51 here. So are we doing okay so far with these push and pop operations? So we still end up with, okay, so let me ask, how many items remain on the stack at this point? Here. Okay, so you have to remember everything that is below the stack pointer is not in use. So everything that is at the stack pointer and after where the stack pointer points to, those things are still in use. So how many things are still in use on this stack? Two items. Yep, exactly. Is that okay? So how does this have anything to do with the concept of calling and returning? Yep.
When you have a program running, don't you have like a call stack of things to be run?
Yes, it is. It is called a called stack, but how does it work? Why does it have anything to do with this order of operating? I know you're I know what you're thinking of, and you are probably on the right track, but I do want to ask the question. Yep.
I mean, I can think of one usage, or I mean, one of its usage would be when you do a recursive call, and then so the function, you have that organized way of going through all of the functions, or going through a function recursively.
Okay, you don't even need recursion. Now, recursion does require this kind of structure a lot, but I can illustrate it with just a few different functions. So let me go ahead and just write these functions. So I'm going to use online GDB, just because it's easy to use and everything is, it's just a whole lot easier this way. All right. So I am going to define a few functions here. So I'm going to define void f, and then f calls g. And then I'm going to define g here. G, on the other hand, would call h. And then function h here doesn't do anything. It does not call any other subroutines. And it just doesn't do a single thing. It just kind of sits around doing nothing. All right. So in main, I don't even need to do the printf here. So I'm going to have main to call f, and then I'm going to have main to also call g, and that's about it. Okay, that's the entire program. So this program doesn't do a single thing that's useful, but it is still going to be useful to illustrate, how calling and returning has something to do with the stack. So we'll go ahead and specify this is written in C, and then we'll go ahead and debug the program. And we'll put a breakpoint on the first line in main, just so that we have a place to stop. So now we run, and it has now stopped at line 26. Okay, so the first thing we want to do, or the first thing I want to do, is to illustrate there's a really useful command in GDB that can help you visualize what is on the stack. And that thing is actually, I'm just trying to find out here, call stack. There we go. So the call stack, which is already displayed here, is already showing you that we have one invocation of a function right now, and that's main. Main is just a subroutine. It is not really special in any way other than it is the first function to be called. Other than that, main is just a function just like everybody else, just like all the other functions in C. Are we good so far? So since my breakpoint is right here, if I single step, okay, if I step into, now single stepping in this case is stepping into and stepping out or stepping over makes a big difference. Because in this case, stepping over means I am going to call function f, and I'm not going to stop until we get to the line right after the function call, which defeats the whole purpose of this experiment. So what I'm going to do is to do a step into, which means if I'm calling a subroutine, I'm tracing, I'm single stepping through the calling of the subroutine. Is that okay? All right. So you can use the key here, which is stepping into, and right away we can see on the call stack that now we have two invocations, right? Because we can see how main is first invoked, and then now we have function f being also invoked, but it's invoked by main. Are we doing okay so far? Is all good? And we are now currently stopping here. So if I single step again, or if I step into again, I'm going to get into G. And what do you think is going to happen to the call stack? We'll see three function calls, right? We'll see three active function calls, and then we have G on top of F, and the F on top of main. So we go ahead and step into again. And there we go. And sure enough, now we have three items. And function G is going to call function H. Okay, fine. This sounds kind of all right. Are we good so far? So we got four items on what we call the call stack. But here's the trick: is what happens when I return from H? If I return from H, what is going to happen to the call stack?
We'll pop H.
It's going to disappear.
Yeah.
Right? Okay. So let's check out. Is that going to happen? Huh, it did. And if I were to return from G here, what's going to happen? G disappear from the call stack. And if I were to call continue execution now, then F is going to disappear. Back to main. So if you think about the ordering of how things appear and disappear on the call stack, it is definitely following the last in, first out fashion. The last function that is called is the first one to return. The first function that got called, which is main, is still here, okay? Because I have not gotten to the return 0 yet. Is that okay? Because I do want to illustrate, how the stack, the discussion of how we move items on the stack correlates to calling and returning. Is that okay? All right. So now we want to, get back to the slide here. So now this has to do with, what do we do when we are calling and what do we do when we are returning? So let's go ahead and try to write a subroutine corresponding to the code at the beginning of this entire module, which is this particular program. So I will write the program on the side, and let me go find the right terminal for that. Nope, not that one. Did I close the terminal? Okay, that's okay. I'll just make a new one. Drag it over here and make it a little bit larger. So what we'll do is I am going to display side by side. So we'll go ahead and look at, I cannot remember whether it's lowercase o or uppercase O to do it side by side. I'm going to try it lowercase o. So we'll have, call, let me go to the temp folder first. One is called .c, which is the C code. The other one is called .ttpsm, which is the assembly code. Nope. Not the right way to do it. Okay, so Q again. So it's uppercase O to display side by side. There we go. Okay. So the C code is nothing new. The C code is just going to be the same thing that we saw earlier. There we go. And then the assembly code is going to imitate the C code. Okay. The first thing we're going to do is to put a no op here. The no op is important if I want to use the command line way of executing a program to generate a trace, which I intend to do in this class. And then the first thing I also need to do is to say, let's just continue execution right away in main. Because if without this, it's just going to continue execution. The subroutine F is going to be here, and then the subroutine main is going to start here. We know one thing for sure, because when main is all done, I have no place to return to. This is in the TTP, the text toy processor. So there's no operating system to return to. There's no command line interface to return to. So when main is all done, we're just going to execute a halt instruction. There's nothing else that I can do. Is that okay? The other thing I need to do is to initialize the stack pointer. Well, that becomes a problem, because where am I going to put the stack? As it turns out, the way I'm going to allocate the stack is anything that is other than this program, I'm going to use all of that as my stack. So that means the highest location of the stack is 255, location 255, because that's the number of locations that I have in RAM. Is that okay? But how should I initialize the stack pointer? I need it to be 1 byte past the end of the array, remember? So if the end of the array is at location 255, what is one location past location 255? 256, that is correct. But remember, everything is modulo 256. So that means 256 is the same thing as 0. I want to initialize my stack pointer to 0, okay? So I'm going to say initialize stack pointer to location 256. But, okay, that's the first question, is, 256 is just 0. The second thing is, what am I going to use as my stack pointer? So that turns out to be an interesting question to ask, because it depends on the architecture. If you're talking about the Intel architecture, then it has a dedicated stack pointer. But TTP is not an architecture like that. All 4 registers, A, B, C, and D, they are equals, okay? If you can do something to register A, you can do it to register B, you can do it to register C, you can do it to register D. So that's why those 4 registers are called general purpose registers. In some other architectures, such as the Intel architecture, we have special purposed registers. So the stack pointer can only be used in certain instructions. It cannot be used in some other instructions, or I should say other registers cannot be used in the same kind of instructions. But in this case, we have a general purpose register architecture, and as a result, I'm just going to make this a made-up rule and say register D is designated as the stack pointer. Is that good? Is that okay? If you guys are all thinking, but why not register C or B or A? Well, that's just because TAG just randomly picked one and decided to pick register D. Is that okay? All right. So we'll just say that TAG chose register D as the stack pointer. So that means I can use an instruction like this, LDID, with 256. Now, 256 is really just 0, okay? So you can also say, that would do the same thing. Is that okay? Because I do want to initialize the stack pointer before I use it. Okay, so after I initialize the stack pointer, I look at the 2 things that I need to do in main and go like, okay, I need to call F. That seems pretty easy. JMPI to F, that should do it. That should continue execution in F, which is just a label at this point. Does that make sense? So execution will now continue in F, which is not supposed to do anything. And now I have to say, where am I supposed to go back to? That becomes a problem, because I mean, the subroutine really doesn't know where to go back to. There are 2, you cannot use a JMPI instruction, because I talked about this a little bit earlier. The first time you return from F is supposed to go to this line, which is where we find the second F, or second invocation of F. The second time f returns, it needs to go to the return statement. So JMPI is not going to get the work done because JMPI has to go to a location that is predetermined by assemble time. This is going to be determined by runtime. Until we run the program, the subroutine F would not know where to go back to. That's a problem. But Tech, you did talk about the stack operations. Maybe that has something to do with this. And indeed it does, okay? Because now we're going to use the stack so that we can use it to remember where the subroutine is supposed to go back to. Is that okay? All right? All right, so that means that all has to be done before we perform the JMPI instruction. We have to now say save return address on stack. I should not use the word save, I should say push. Okay. But where am I supposed to return to? How do I designate that location? Well, we know that there are two jumps, right? There are two JMPI to F, one corresponding to the first call of F, the other one corresponding to the second invocation of F, right? So that means, if I were to put a label here, and I can say, return point 2, return point 1, this is return point 1. So this label, return point 1, is the address of this JMPIF instruction. That seems to be a good place to go back to when the subroutine is done. Don't you think? Yes? Okay, because after all, in the C code, when the first invocation returns, I'm supposed to call F again. Okay? All right, so now what are we going to do to push the return address on the stack? Well, let's go back and check, what we're supposed to do in the module over here. So the first thing we need to do is to decrement the stack pointer. Okay, let's see how we can do that. So let me see if I can display both the editor and the slide or the module at the same time. Yes, we can, indeed. So the first thing is to decrement the stack pointer. So tell me, what do I do here to decrement the stack pointer? Stack pointer is just register D. I think the way I described it kind of described the mnemonic already. What did I say again?
Decrement D.
Decrement D. Very good. So we have a decrement D here, which is the same thing as SP minus minus. Okay. And then the next thing we need to do is to store whatever value to the location that the stack pointer is pointing to. How do we do that? This is a trick question, by the way, because whatever you're thinking is not, well, okay, I shouldn't say not, because some of you may know that already, but whatever you're thinking may not work right away. So what do we do here? First of all, are we reading from RAM? Okay, first of all, is this operation, let me highlight it first. Is this operation relating to RAM at all? Is it relating to memory at all? Well, I think the key question here is, what is this doing? What is the asterisk? What does it represent? Is it a really badly formatted multiplication?
It's a value at a certain location, right?
It's dereferencing. Yes, go ahead.
Is that the location on RAM that it is? So
it is the location that the stack pointer is pointing to. Okay. And this is an assignment operation. Okay. This entire expression here is an assignment, which means we evaluate what the right-hand side is. The right-hand side is easy. It's just the return point 1 over here. What are we doing to that value? It's an assignment, which means we have to change something. An assignment changes the left-hand side to the value provided by the right-hand side. What is the left-hand side? What is this representing?
The 255th memory address in RAM.
Only one of them. Whatever the stack point is pointing to. The stack pointer can only point to 1 byte at a time because of the way it is defined here. So the 1 byte that the stack pointer is pointing to is the one that is going to be changed to whatever that label is. Are we okay so far? Okay, so let me repeat a question that I asked earlier. Is this operation related to memory? Am I doing something with memory? Yes. Okay. Am I reading or am I writing? Am I writing to memory, changing the location, or am I reading from memory, which is retrieving the content of a location? Right. We are writing. Very good. Of all the instructions, of the TTP, there's only one that is capable of storing something. And which one is it? Hmm? That's not an instruction. Okay, so let's see if we can find that. Okay, we go to the share folder, we go to processor, and then we go to the opcode table. And we focus on column C and see if we can find something that resembles what we are trying to do. So which one do you, okay, I did not intend to change it. So which one here resembles what we are trying to do?
Line 34.
Sorry, go ahead.
Line 34.
And
I said LDI, but.
LDI? No, LDI is only reading from memory. So if you look at LDI, where's LDI? LDI is right here. The dereference is on the right-hand side of the assignment, which means we are only reading from something from memory to change something else, which turns out to be a register. So that's not the answer. LDI is not the answer, but that's good. I mean, that's, close. And line 34 or row 34 is the answer. It's a store instruction. The store instruction says register X, is going to provide a value, and we're going to use that value to overwrite whatever register Y is pointing to. Because remember, X, Y, they both have to be one of the 4 registers, A, B, C, or D in the register bank. So now we can say, we can use one register to provide the value, use one register to point to the location where the location is going to store the value of the register. Is that okay so far? So we need a store instruction. But getting back to our example, so what are we going to do? We know this is going to be a store instruction. So the question is, what am I going to put inside the parentheses, and what do I put on the as the second operand of the store instruction? So we're trying to match this instruction to what we want to do, which is pushing the return address, which turns out to be the label of RETPET1, return point 1. So how do we do this? We're almost there, right? Because if I were to kind of remember to do this, in the C notation, the C notation says we are dereferencing the stack pointer so that it stores whatever the return address is, which in this case is really just a label of PT1, return point 1. So that's what we want to do. Okay, the comment on this line tells us what we want to do. The question is, how do I format it so that it works here? And remember, I said this was a trick question. Yes? Correct. So what do I put inside the parentheses? I cannot put SP because SP is not a register. So which register did I choose to use as the stack pointer? Register D. Okay, so register D goes here. Okay, that answers one of the 2 questions. And then the second question is, what do I put as my second operand? And you guys are going to go, we can do this. But that won't work. That won't work because the second operand, according to the opcode table, has to be what? It has to be an X, which means it has to be a register. If it is an I, okay, then it can be any immediate value, which can be a label, but no, this is an X. Gentlemen and ladies, this is the reason why I teach the class the way I do. Because if I were to teach just the language itself, the assembly language itself, it would be impossible or very, very difficult to understand. Why can't we just use a label here? Why do we have to use a register instead of a label? The answer is, it is limited by the pathways that I can establish inside the processor. There is no way okay, I can directly connect a location of RAM and route it back to a location in RAM, because that's what it's boiling down to. Because if I were to do this as an STY and then an immediate, the immediate itself is living in RAM, and I'm trying to use it to change another location in RAM that is pointed to by a register. I can't do that, not easily, okay? So this is the reason why the architecture is designed the way it is, and the instruction for column C, the mnemonic, is simply a way that makes it easier for us to specify the instructions. But you cannot just say, well, but why do we use a register here? Why can't we just use a label? That's because the architecture does not support it. Without introducing the architecture first, then people would not understand. But I thought we just have to put a label at the location that the register D is pointing to. It sounds simple, but it cannot be done. Okay, so that means I cannot do this, okay? So what do I need to do? This part here has to be a register. So what do I need to do?
You can load the point one onto another register.
That's right, okay? And in this case, I get 3 registers to choose from. Register A, B, or C they will all be fine. And then I change this to refer to register A. And it's the correct solution. It looks kind of awkward, but that's the way it works. Are we okay so far? So right now, these 3 lines of code, decrement D, LDIA with return point 1, and an STDA, is going to push the return address on the stack. Are we good so far? All right. And then we continue execution to F. So when we get to F, the subroutine F says, I got nothing to do. I'm ready to go back. How do we get back? From the perspective of the subroutine, how does it get back? Now, yes, go ahead.
Stack pointer.
It has to utilize the stack pointer somehow. Okay, very good. So let me describe what it needs to do. Okay, it needs to pop the return address first. Okay, so how can it pop the return address? Okay, wait. Let me try to remember how to pop something from the stack. So to pop something from the stack means I need to designate something to store the value, but nonetheless, the idea is wherever the stack pointer is pointing to, go to that location, retrieve the content at that location, stash it to something called X here, and then we increment the stack pointer. Is that okay? Where do we get this code from? From here. This is where it got it from. Okay, so when you look at these 2 lines here, that's the same thing as what we specify over here when we want to retrieve or pop a value. Okay, one thing at a time. Let's deal with SP++ first. How do I increment the stack pointer? Well, first of all, what is the stack pointer again? It's register D. Okay, very good. So how do we increment the value of a register? Yep, the increment instruction. Increment D is going to do the SP++. Easy peasy. Next, how do we do something like this? Yep.
Load A, B.
Okay. So we can designate any of the 3 remaining registers. A is fine, like that. Are we doing okay so far with LDAD, which is load? It's not load immediate, because we don't know exactly where we're supposed to get the value. It's just whatever the stack point is pointing to at that moment when we execute the opcode. So where it actually goes to retrieve the value to store into register H is only determined at runtime, whereas LDI is determined at assemble time. So that's the main difference between LDI and LD. Is that okay? All right, next thing is, so great. Now we have A's, storing the return address, what are we going to do? Well, okay, I know what we want to do. We want to continue execution at the location that A is pointing to, right? Because after all, at this point, where the blinky cursor, well, it's not blinky, where the cursor is I already have the return address in register A. And it is called a return address because that is where I need to return to in terms of execution. Is that okay? And which register, inside the processor, dictates where to get the next opcode. The, in some architecture, it is indeed called the instruction pointer or IP, but in text toy processor, it is called program counter. Very good. Okay, so the program counter and the instruction pointer are basically the same thing. Different architectures have slightly different terminology, but it's the PC. Okay, so I'm going to write down here and say, this is all I really want to do. I want to copy the value in register A, which is where I'm supposed to go back to, change PC. So this way, the next fetch, is going to go to that new location that I'm supposed to go to. Okay. And which instruction do you think is going to do this trick? Well, we haven't talked about this one. Okay, so if you're scratching your head and go like, I don't remember any instruction that can do this. Is that kind of like CPR, PCA? No, it's almost like that, but it's not. Because if you were to use CPR, the first operand has to be one of the 4 registers, A, B, C, or D. So there's no such thing as a CPR PCA because PC, the program counter, is not inside the register bank. Okay, scratch that idea. Right idea, just not possible to specify. So now we go back to the opcode table, and I think it is here somewhere. So which row do you think is going to do what I want to do? Which is just saying, hey, the program counter, I just want you to copy that value from that register over there.
JMP.
Which row? Which row?
28.
Row 28 is correct. Very good. So row 28 is what we need to do. So you can now see that, but isn't that the same thing that we have before JMPI? No, the I makes all the difference. So let me just compare and contrast between JMP and JMPI first, and then we're going to go back to what we are talking about. This is JMPI. So you can see in JMPI, the program counter is updated by whatever it points to. Is that okay? On the other hand, when we have JMP, the program counter is just saying, hey, one of the 4 registers, specify which one is supposed to provide the value to change the program counter. So this is a whole lot more direct, okay? This is basically, you can now directly control where you want to go to. And it is determined at runtime. It's no longer determined at assemble time. JMPI, where it goes to, is determined at assemble time because the I is an immediate value, which is a constant. In this case, the value inside register X, it can be register A, B, C, or D, is a runtime thing. Whatever that register has at the moment that you execute the JMP X instruction is where it's going to go. Is that okay? Okay. Let me go back to the code and just finish this first. This is JMP A. I'm using register A to tell me where to go to. So I'm just going to pause here to see if there are any questions. Because right now we have the subroutine F and also the code to push, both in view in the editor at the same time. So can everybody see how we use register, how we push the return value with these 3 lines of code right before the JMPI, and how we use the 3 instructions at the F colon label to retrieve the same thing? And I know how some people think. They are optimizers, because I do have optimizer people in my household, and they're going to go like, why can't we just use register A? I mean, looks like we're just using register A. Okay. The problem of using register A itself to remember where the return address is how many registers do we have again? We only got 4, right? So if you use a register to communicate where to return to, it's going to be very limited, okay? So what this means is I have no restriction of having to use register A here just because I use register A over here. I can change this register A to B or C. Okay, let's change it. All I have to do is to make it consistent, like that. Down here, I don't have to use register A. I could use register B. I just have to be consistent. So this is register B, register B. I just have to be consistent. Is that okay so far? You good? Okay. So now we are now at the second point of calling. What should I do before I jump again? This instruction here, this JMPI to F, is the beginning of the calling, the second invocation of F, the second calling of F. So what should I do again? Every time we call a subroutine, we have to save or push the return address. Is that okay? So if I were to push the return address, where do we think the second invocation of F should return to? Which instruction should it return to, I should ask? The halt instruction. Very good. Okay. So it sounds like we can have return point 2 to be defined here because we do want the second invocation to continue execution where the halt instruction is. Okay. So that means the rest is kind of the same deal because what I need to do now is to say, okay, we have to push return address on stack again. Okay, we always start with decrementing the stack pointer, and then I'll just kind of mix things around a little bit. This time I use register A. Okay, PT2 return point 2 stda. So these 3 instructions here will save the return address on the stack again. But by the time we get to the subroutine F, it's going to use its own 3 instructions to retrieve the return address to get back to where the return address is, which in this case is the halt instruction. It's just one line past the view of the entire program. Are we doing okay so far with this explanation? Are we good so far? Okay. So next, we're going to run this program. Okay, we're going to run the assembly code through the command line interface of Logisim, and then we'll look at the trace. Okay, we'll look at how things are changed in the analysis tab of the assembler. Okay, because that is how we can get a better understanding of exactly what is going on, who is doing what. Okay, so let's go ahead and check that out. Okay, save this, and now we can go back to my CISP processor. Nope, this is River Spider. There we go. And we'll go ahead and submit the code called call.ttpasm. All right, it's all done. So now we can go back to the assembler. The assembler is not even up and running yet, okay? And yet it can do everything in the back end because it's doing all the updates, in the back end. So by the time we get here, it's all done already. Look at the source code. That's the source code that we were working with. And then when you look at the analysis tab, this describes exactly what went on when the program executed. All right, so let's see if we can find out exactly what is going on. And I would encourage you to take a snapshot of this code like right now, okay? Or whenever you have access to your Google Drive, is to make a snapshot of this because this is studying material, okay? If you want to quote unquote study how subroutines are called and how a called subroutine returns. This is the I should call this is the companion to the actual description, which is here. The description is dry and boring. Okay, it doesn't really illustrate how things happen, but this one does. Okay, if you go to the assembler, it does show you exactly what is going on. Location 00, that's my no op. Okay, it has to be here in order for this tool to work. Okay, so don't ask me why we have it here because it's a bug in LogiSim. Location 01 is a JMPI to main. In other words, I skip around the code of the subroutine so I can actually start with the main subroutine. Okay, so main as a label is starting at location 06. And the first thing it does is to initialize the stack pointer to 00. Do I have to do this? The answer is no, because when you restart the simulator, all the registers got zeroed out anyway. But I want to put it here. And then we try to push the return address, which is return point 1. The first thing we did was to decrement the stack pointer, and now you can see, oh, we are not going to store anything to location 00, which we have been bad. We are actually going to store something to location FF. And then we use register B to store the return point 1, okay, return point 1 as a label. That turns out to be E in hexadecimal. And then we do the ST instruction. The ST instruction, which is at location 0D, is I'm using 0E as a value, which is coming from register B, to change the content at location FF. And that's the notation that I'm using here. You can see how I'm using an asterisk here to mean it is dereferencing. I'm changing the location, the content at location FF to 0E. Is that okay? All right. And then I have a JMPI instruction. So 0C is corresponding to a JMPI instruction, which JMPIs to F as a label. F as a label is the same thing as 03. So at that point, I'm going to go to the stack pointer and ask, hey, what are you pointing at in RAM? I'm pointing to a location that has 0E as its content. Oh, good. Give it to me, and I'm going to store that to register C. That's the LD instruction at label F. And then we increment the stack pointer. The stack pointer was FF. It is now incremented back to 00. And then when we get to 05, location 05, that's our JMP instruction, not JMPI, but JMP, which basically just says, hey, register C, I'm going to use your value to update the program counter. In other words, at location 05, the program counter gets changed to 0E, which means the next instruction is at location 0E. That's how we jumped all the way back to the return point 1. Is that okay so far? Kind of? Maybe? All right. So what do we do? Same thing, okay? Decrement the stack pointer, copy the label to a register. This is return point 2. And then we copy or we store the register A. We store whatever is in register A to whatever register D is pointing to. This is how we push. Then we continue execution at the subroutine, which is F, the label. And then what we do is we retrieve whatever the stack pointer is pointing to, which is 1,4, to register C. Then we increment the stack pointer. That completes the pop operation. And then at 0,5, we do a JMP C. So it continues execution at wherever register C is pointing to, which is location 1,4. Location 1,4 has the halt instruction. And that ends the entire program. Is that okay? Now, if this is the first time you read the module, it's going to go over like this. Okay? I can totally understand that. But that's why you need to kind of study. How do you study with this kind of material? Reading this over and over again may help a little bit, okay? But trying to understand how the trace itself works, which is here, is going to be more beneficial. Is that okay? Now, if you want something that's even more beneficial, I will give you an ungraded assignment. So let me give you an ungraded assignment. So we'll go ahead and call this, gf.c. I want you to do this, okay? This is function g, that doesn't do anything. This is function f, and the only thing it does is to call function g. Oops. And then here's main, and main is going to call function f, and then it will call function g also, and then return 0. I want this to be your ungraded assignment, and I will do this before Wednesday, because today we talked about the concept, practice it, so that on Wednesday we can actually utilize this concept to build something else. And obviously I'm going to show you the code on Wednesday as well. Is that okay? So I got a few things to mention before I kind of move on to the lab of today. One, it doesn't matter where you're calling and who you're calling. The way you do it is the same. Push the return address and then do an unconditional branch to the subroutine. And when you're returning, it doesn't matter where you're returning to, it's always the same step too. Pop the return address and then continue execution at the return address. Are we good so far? More or less? Okay. But I would start with this, okay? If I were studying for this material, I would start with this, okay? I would take a snapshot of this particular assembler spreadsheet, just kind of freeze it and call it, give it a name, okay? Give it a name like, calling and returning, something like that, okay? And then once you have that, I would use your column, the other columns, column F is fine. I would use column F to kind of explain what is going on as we execute each instruction. What does it mean? What is it doing? What does it mean in this context? Okay, and what is the implication? Okay, all of those are going to be important. And I would also note every change to locations in RAM and go like, what am I storing here in RAM? And once again, what am I storing here in RAM? How do I know where to store and what to store? Okay, so if you can answer all of those questions comfortably, then I would say, yeah, you probably understand how calling and returning works. Are we good so far? Can I give you some depressing news? Well, okay, that was not really a question, but the depressing news has nothing to do with the exam, okay? It has to do with the instruction set, okay? So let me go back to the instruction set that I had worked out earlier, which is call.ttpasm. These three instructions here, load, increment D, and JMPC, in most architecture, it's just RET. It's just a return instruction. It would do all three things for you with one single opcode or one single instruction, but the TTP does not have that, okay? And then the other thing is when you look at decrement D, LDI, B, blah, 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 ST, and then JMP, I to F, in most architectures, those 4 lines of code is simply call F. But we don't have call F in TTP ASM. You kind of have to do it in these 4 instructions. Some of you are thinking, but why? Because if I just say there's a call instruction or there's a return instruction, you don't need to understand what's going on behind the scenes. And if you don't understand what is going behind the scenes, you don't understand what the stack is useful for. And if you don't know why the stack is useful, or how we store the return address on the stack, then you won't be able to debug some of the C or C++ program where you are accessing an array out of bound and you just end up accidentally trashing the return address itself. So there are reasons for all of those things. I said it's depressing only because it does make your program look longer and a little bit more complex. But it does boil all the concepts down to the most elemental steps that you can perform. Question?
This is a lot more lower, this is a lot lower language than I had expected, which is pretty good. Like, it really gives you that understanding of what's going on.
I think at some point I can give you guys some examples, like what kind of weird behavior you can expect when you access an array out of bound. Now that is not easy to demonstrate because it depends a lot on the compiler. So I have to first figure out how a compiler utilizes space on the stack. And then I have to figure out how to artificially trash a location that I'm not supposed to in order to produce the symptom that I want to show you. So I have to reverse a whole lot of steps. It's kind of like reverse hacking, because hacking means you have a program, you want it to behave in a certain way. I'm starting with the opposite, which is I want to know how the stack is used so that I can achieve the behavior that I want it to do. So let me think about doing that, because I think once I illustrate that example, which only has C code, but will give you a symptom that is like, I don't know how this happens, then I think more of you can be convinced that this material is useful beyond this class. All right, so with that said, I am going to release the lab for today, which is called Compiling C Control Structures. And I think I only have to release by showing you the passcode or the access code. The access code is present. And I already got the due date and time set up, so I can now save and publish. There we go. All right. So you guys can go ahead and do the lab. It should not take too long. This one does not require you to actually write code. You do have to understand code, but you don't have to write your own. And then we'll see what the computer club has decided to do.
I don't know if he emailed you. I have to go call him, but Callie's not here today, so it's just going to be us doing lead codes again.
Okay, sounds good. Are you planning on the problem 121?
Yeah.
That's a good one. It's very deceptive. It looks simple, but it's not.
I was trying to find something that'd be more like real world interesting instead of just normal data stuff, because that seems to bore everybody.
Well, in real world, you cannot go back in time and figure out when to buy and sell the stock. Unless you got time travel done. Okay, all right. So I'm going to stop the recorder and upload it.